right, finishing talking up a little about the kinetic theory of gases, and then we'll talk about mechanisms of heat. So last class period, we worked out the derivation for the kinetic theory of gases to see that the average, remember these little greater than, less than, we call them brackets, at least in physics, means average. So the average kinetic energy is equal to 3/2 K, where K is that Boltzmann constant, multiplied by temperature. What unit should you use for temperature in this equation? Kelvins. If it's a change in temperature, Celsius or Kelvins, either one is fine. But if it's just temperature, go with Kelvins. So that's the relationship between temperature and the kinetic energy for what type of material? Okay? This was done for an ideal gas, and in fact, this is only, notice the TR, it's the translational kinetic energy. The translational kinetic energy is the only kinetic energy only if it's monatomic, right? If it's diatomic, I talked about last class where you have rotational or vibrational kinetic energy as well. So this is, for monatomic ideal gas, you don't have to put the TR because that's the whole thing. Otherwise, you need to be aware. The average translational kinetic energy is 3/2 kT. So if the average translational kinetic energy is 3/2 kT, and I have capital N molecules, what would the total kinetic energy be? The average is this, and if I have N molecules, what's the total going to be? It's going to have this number multiplied by N. So we will learn coming up very soon, like, I don't know, Wednesday, that the internal energy for a monatomic ideal gas is equal to 3 times, or not 3, N, that's an N, times that value of 3/2 kT. But if it's a monatomic ideal gas, I'm also going to have the ideal gas law applicable. And so that's also equal to, NKT is equal to PV, 3/2 PV. So that's an equation we're going to use if it's a monatomic ideal gas. The internal energy is 3/2 NKT, or 3/2 pressure times volume. Excuse me. So we have here kinetic energy, 1/2 mass times speed squared. The average of that is proportional to the temperature. That means that we can do something to learn about the speed from the temperature. All along, I've been saying that the temperature is really telling us how fast the molecules are traveling. So if I take this and I solve it for speed, first thing I can solve for is speed squared average. So V squared average is equal to, I'm going to have to take both sides and multiply by 2. I'm going to take this and just solve it for the V squared average. So I have to multiply by 2 and divide by M. So I'll take the term on the right, which was 3/2 kT, and multiply by 2, divide by M. And at this point, a lot of people would like to say that the average speed is just the square root of this. But that's not correct. And I'm sure there are plenty of people who know why that's not correct. So I'll ask somebody, can somebody tell me why it's not correct to say that? So I'm going to put a not equal sign so we know it's not correct. Why is that incorrect? Because the square was inside of the average, not outside of the average. So this is, the difference is if I have the numbers 1, 2, and 3. The average of 1, 2, and 3 is, of course, 1 plus 2 plus 3 divided by 3 is 2. But if I take the average of the squares of those numbers, that's going to be 1 squared plus 2 squared plus 3 squared, all divided by 3. That's going to be 1 plus 4 plus 9 So 14, divide 14 by 3, and you have 14 divided by 3 is 4 2/3. And if I take the square root then of 4 2/3, that's not the same value of 2. It's bigger, right? And in fact, you're always going to have that. You're always going to have the square root of the average of the squares is bigger than the average. Because you squared the values, you gave a higher weight to the bigger values when you did the average of the squares. So when we take the square root, we call it the root mean squared. And root mean squared, you actually do it in the reverse order. So what it means to do a RMS is you first square the values, then find the mean, which is just a word for average, and then you take the square root. And so that's why with my average of 1, 2, 3, square them, 1, 4, 9, take the average of those. So I have the average now, so I did the squares, I did the mean, and then you do the square root. I spent a lot of time on this. I know probably 80% of you know what RMS means, but just to make sure that people don't get confused between the average speed and the RMS speed. So the distribution of molecules, you have all these molecules, in the room or whatever, bouncing around off of each other. Every time they bounce off of each other, you're going to have some exchange of energy and momentum. Now, if they're elastic collisions, the total kinetic energy is remaining the same, but you're distributing energy. And so once again, statistics will allow you to determine what the distribution of speeds will be. And so James Clerk Maxwell and Ludwig Boltzmann, they did the statistical work to come up with an equation that's shown right here that tells you what the probability of having a given speed for molecule and gas will be if it's an ideal gas at temperature. Okay, I can't do it for the temperatures, so I'm going to put missed. At speed V, so V is 2 places, and at temperature T. Temperature is also 2 places. I can't highlight it because there's a problem, but so you have different temperatures makes a difference. Different speeds have then a different probability. And so if you graph those out, the picture on the right shows what changes if you change the temperature. If you have a higher temperature, T2 is the high temperature, the peak here is a higher speed. We call the peak the most probable speed. So the most probable speed is faster if you're a higher temperature. And of course, your fastest speed is also higher if it's a higher temperature. The lowest speed is still going to be 0. If you cool it down, the speeds slow down. So the most probable speed goes to a lower speed if you cool it down. The picture on the left, which I'm now going to zoom in on, shows us 2 of the 3 important speeds we actually talk about. The most probable speed. The most probable speed says the speed that the most molecules have is that most probable speed. And so it's just the peak of the probability curve because it's the most likely. The RMS, I said it's always faster, so it's over here to the right. In the calculus-based class tomorrow, we're going to go through and do the calculations to show this. But it turns out if you have this Maxwell-Boltzmann distribution, the RMS speed is always going to be 1.22 times the most probable speed. So there's a fixed mathematical relationship because you have a fixed equation for the probability. The average speed, which of course we've been writing like this, is slower than the RMS speed, but faster than the most probable. So the average speed would be somewhere around here. And it's always, again, going to be 1.13 times the most probable speed. So from the temperature and the mass of your molecules, you directly can calculate the RMS speed. And then assuming it's an ideal gas, you can from that just use the distribution to calculate what the average speed is or the most probable speed. So this is useful. As you might have guessed, the calculus we're going to do tomorrow is a little bit interesting because we're taking integrals of a function that has v squared e to the minus 1/2 mv squared over kt. But we can do it. Don't give him grief, Jordan. He'll do it. All right, so that's what we call the maximal Boltzmann distribution of speeds. Now, I'm going to come back to this picture, but first I want to talk about evaporation and then come back to it. Right now, as you can see, I'm up here sweating, sweating like a horse that's been run hard. Water is coming off of my skin. What is that doing to my body temperature? It's cooling it. Everybody knows that. Now, a few years back, Corey Stringer was at football practice, and his body overheated and he died. You guys remember that? His body overheated because he didn't cool properly. God created us with a cooling mechanism. We sweat, and that sweat helps us cool. And there are two things that would stop that. Number one is if you have clothing that makes it so you can't have the water evaporate. Or number two, if you're in a high humidity situation. So I want to come back now to this. Well, first look at this and then go back to that distribution. When evaporation occurs, you have water molecules that come to the surface between liquid and gas, and they have a high enough kinetic energy to break free. Remember we talked about the surface tension? I said it has two names, surface tension and surface energy. It's actually the same numerically, it's just different names. Well, if you have a molecule with a kinetic energy higher than the surface energy, then it has enough energy to break free of the surface when it gets to the surface. And so it will evaporate. If you have one that's slower, doesn't have enough kinetic energy, it can't get out and it stays in. So if we look back here, so let's just look at the picture on the left here. We can say, okay, corresponding with the surface energy, there's a certain speed. If you have this speed, it has enough kinetic energy to break free. And so I can just arbitrarily say, what if that speed, the speed necessary to break free, is right here? So any molecule that has a speed above that, when it gets to the surface, will break free. Not every molecule above there will break free because it has to get to the surface. But any molecule that gets to the surface at a speed above that can break free. Are there molecules that are going to have speeds above my black line? Yes. So if I have a molecule that has a speed out here and it gets to the surface, it evaporates. If I had a molecule with a speed here and it gets to the surface, what's going to happen? It stays in. So in terms of the molecules that evaporate, which ones evaporate? The ones with the higher speed or the lower speed? Very simple question, not a tricky one. Higher speeds evaporate. In terms of temperature, which ones are they? Higher temperature. So when you have evaporation, only the higher temperature molecules can escape, leaving you with the lower temperature molecules, which means the average kinetic energy or the overall temperature has to go down for each evaporation. So the water that's left on my skin is cooler because only the hottest molecules were allowed to escape. Well, if that water on my skin is cooler, then my body is going to put heat into the water. Heat is the transfer of energy to bring it up to the same temperature as my skin. And so I'm going to have heat that flows out of my body. And when heat flows out of my body, I feel a chill. And so that's why you have the cooling effect from evaporation, because the hottest molecules escape, and then your body replaces that energy so heat flows out of you, and it cools you down. Now, it's only like 2 slides from here. If the humidity is 100%, that means you're going to have the rate of molecules leaving is going to be the same as the rate of molecules coming back in, which means that you're not going to have any net cooling because you're bringing in molecules as quick as they're leaving, and on average they're going to be same temperatures. You don't have evaporative cooling. So, I grew up in California. Swamp coolers are reasonably popular there. A swamp cooler is basically you run water over some pipes, and that water running over the pipes cools the pipes, and you cool your house that way. Doesn't work very well here in Nebraska because in the summer when it's hot, it's also humid. Because it's humid, you don't get very much evaporative cooling, and hence no work. If you're in Southern California or Arizona, where the relative humidity might be 5 to 10% during the summer, well, then it's going to be very effective. Okay. First clicker question. How does the average speed compare to the RMS speed in a gas? Okay, I'll give you about 10 more seconds. All right. Well, we have a reasonable distribution. 10 to 33. And for some reason, it doesn't show a fourth option. But that's okay because we don't need more information. So we do have a majority. Larissa, tell us what you answered and give us your reasoning.
I said C. I don't really have a good reason though.
Okay. Well, let's talk about the 3 speeds that I mentioned. I mentioned the V most probable, the V RMS, and the V average, otherwise written as like that. What does the most probable mean? I mean, you can just take the words if you like. What does it mean? It's actually not exactly the same as the mode, but essentially the same, right? Because you don't have distinct values, you have a continuous range. If you were to say how many have this speed, you end up with 0 at any speed.
It's analogous to.
But yeah, it's analogous to. So it's the speed where if you look at a distribution, you have the highest for the distribution. And then the V average is the average. You add them all up, divide by the total. And then the VRMS is if you square them all, add the squares all up, divide by the total number, and then square root. Now, because of the squares, you always have a weighting factor that's equal to the value. So if I'm taking 5 versus 10, 10 would have a weighting factor of 10, and 5 would have a weighting factor of 5. Which one is going to have a bigger effect than on my average of those 2 numbers? 10, because of the bigger weighting factor. So the RMS is always the highest because you have that larger weighting factor. And so then we just have to compare it to, well, this only was comparing average to RMS. So since the RMS is always higher because of that higher weighting factor, then your answer had to be the average is slower, the RMS is faster. And if you put these things in order of speed, probable, average, and RMS is the order, always, if you have a Maxwell Boltzmann distribution. Questions about that? No. Jordan is telling me no one has a question. Okay, a couple diagrams that you see a lot in chemistry and physics. First, the pressure volume diagram. Pressure volume diagrams tell us 2 of our 4 variables of state. What were the four variables of state? Pressure, volume, temperature, and the number of molecules. Now, you guys might have noticed my message yesterday that the last homework problem asks you to find the number of moles, but then it asks you to find capital N. Those are not the same thing, right? What does capital N mean? Molecules. What do we use for moles? Lowercase n. So that problem, they really are looking for the number of moles, but I'm going to go through tomorrow and just grade it by hand so you get credit if you put in capital N since it asks, in the answer it has capital N equals. But just making sure we're clear on that. So these are our variables of state: pressure, volume, temperature, and the number of moles. So this diagram only has two of those values. So we have two remaining. Well, we just say for a gas with a fixed number of molecules. So for these, we just say N is constant, and we're very happy with that. But then we still have temperature. So what do we do for temperature? We have those different lines in the diagram to represent different temperatures. Now, you probably have seen the three-dimensional models. The three-dimensional models are great because you have pressure on one axis, volume on another axis, and temperature on a third, and then you can just, changing the angle you view it at, you can see different views of, which variables are going to affect it. So now we have the red lines are how the pressure and volume relate at a given temperature. Now, if the gas is ideal, we should have PV is equal to NKT. And so for a constant temperature, this would be equal to a constant. So that means my pressure times volume is constant, or my pressure should be proportional to 1 divided by volume. Proportional to, not equal to. Well, if you graph pressure is equal to constant times 1 over volume, you get a shape that looks like this shape here. And so we can look at that and we say, okay, that temperature 5 is behaving pretty ideally because it has the right shape. It has the nice smooth curve for a 1 over V. But if we look here, that has the little jiggle in it. Clearly not behaving ideally anymore. So I can look at the graph and say that's not ideal because it's not following the shape that I should have from this equation. And so these here are non-ideal. Now, just to review, what were the properties that made a gas an ideal gas? Okay, many people answered, and I didn't hear a distinct answer. Okay, I heard very clearly no volume. Possible? No. Approximately possible if the density is small. So that's one condition for ideal is we need to have a small density for it to behave ideally. What was the second one? Okay, the second one was they don't interact when they get close to each other unless they actually contact, in which case they have perfectly elastic collisions. Not very realistic, but if you get to high temperatures, they have so much kinetic energy, it's pretty close. And so to approximate that second one, we had high temperature. So for things to behave ideally, we said it needs to be high temperature and low density. So it makes sense that the higher temperatures, notice the higher temperatures of these, are the ones that are behaving ideally. The lower temperatures, non-ideal. The picture on the right, by the way, is just a blow-up of the one on the left. So I can take the one on the left and zoom in, and look, we got the same thing. Okay. Now there's other interesting things to note here. You'll notice I called this a title I had the critical point. The critical point is this point right here. The critical point has the maximum temperature where it's possible to have a liquid. Pressure. Maximum pressure where it's possible to have a liquid. If the pressure goes above that, there is no liquid. There is also a temperature relationship. That's the lowest temperature where it's possible to have a liquid. So you have a critical temperature and a critical pressure. Both are If you have below that, you can have a liquid. If you're above that critical pressure, you cannot have a liquid. If you're above the critical temperature, you cannot have a liquid. So liquids, they only exist in low pressure and low temperature situations with a relative sense. It depends on what the actual molecules are, what those pressures and temperatures are going to be. Okay, enough on this. Let's go to the second ones, the so-called phase diagrams. At least as a physicist, I'm far, far more comfortable with these diagrams. The diagram has lines that are now not indicating how the pressure changes with temperature, but rather it's separating phases. That's the name phase diagram. So in this diagram, S stands for solid, L stands for liquid, and V stands for vapor. Now, some people have different definitions for vapor versus gas. I'm not going to go grind any axes on this. But vapor or gas, means that it fills the space. It's not bound together. If you look at this one on the left is for water. You might notice that I made a mistake 2 lectures ago when I said the calibration point for water was now 0.16 degrees Celsius. It's 273.16 degrees Celsius. There was a reason I had 0.16, but it wasn't correct. Or 0.01, or 273.16 kelvins. Wow, I still made a mistake. Or 0.01 Celsius. So the calibration point is that triple point temperature of 0.01 degrees Celsius, or 273.16 kelvins. The triple point is a unique temperature and pressure where you can have all 3 of those phases coexist. You can have the solid phase, the vapor phase, and the liquid phase all at the same temperature and pressure. You can't raise the pressure a little and change the temperature and have it occur. It has to be exactly there. That's why it's used as a calibration point, because it's an exact temperature that can always be reproduced. Doesn't matter where in the world you are. You have to have the right pressure and you have to have the right temperature. So it's perfectly reproducible. What's unique about water that everyone needs to be aware of is the slope of this line right here. It goes up and to the left. So what that means, if you are at 1 atmosphere, so here's 1 atmosphere, and you are, let's say, at a temperature that is just a little higher than the freezing temperature of 1 atmosphere, if you increase the pressure, like if you have an ice skate pushing on that ice, you increase the pressure, then you're going to go upward. So, okay, you're at the freezing temperature, so you're here. You increase the pressure and you go up here and it goes into the liquid phase. So when you compress water, you can go from ice to liquid, which is opposite of what most things do. Over here on the right, we have carbon dioxide. And for carbon dioxide, the slope is going up and to the right. If you increase the pressure, you could go from liquid to solid. You could freeze it by compressing. Whereas for water, you can melt it by compressing. And that's odd. That's weird. It's important. Now, some people think water always does that, and that's untrue. If you get up to high enough pressure, this line will go like that. So if you get up to high enough pressure, water then behaves normally. And it has to do with the uniqueness of the van der Waals forces that hold the ice together that give it that shape. So we've already talked about the triple point. The next thing to talk about here is, once again, looking at the critical point. The critical point had a temperature and pressure. On this graph, you see temperature and pressure. So the temperature for the critical point is 374 degrees Celsius. The pressure is 218 atmospheres. And above those, you can't have a liquid, which means it's not possible to have liquid anywhere out here, which makes for a real weird dashed line right here, because that dashed line is separating liquid from gas, but it's not this normal separator. If you cross that dashed line, you don't actually notice the difference in the material. If you take a liquid, so let's say we start with water that is right here. If we raise the pressure up to this point, as we raise the pressure, it's getting more and more compressed, right? Then we increase the temperature out to this point. We increase the temperature, they're moving faster and faster. It's actually going to spread out a little. And then we lower the pressure, and then we lower the temperature. We will have moved from a situation that was clearly a liquid to a situation that's clearly a gas. But we would have never seen it condense, or not condense in this case, evaporate. Went the wrong direction for condensation. We would have just seen a continual morphing with no abrupt changes. The density would not have an abrupt change like you see when you go from a liquid to a gas. And so as long as you go around that critical point, you don't see the phase change, even though you can change phases. If I had started at my same starting point and just brought it straight to there, I would have seen, aha, now it's a liquid, aha, now it's a gas. I would have seen that process if I went by a different route. But because I have the same state variables, it's got to be the same when you get to the starting or ending points. Yes?
So in sublimation, when it goes straight from solid to gas, is that the same thing?
Okay, sublimation is what would occur. Actually, that's the wrong one. That would be evaporation where I circled. Sublimation would be going from here to here. It would also be going from there to there wouldn't be as clear of sublimation. You're saying, is that liquid or gas? I don't know, right? It's kind of indeterminate. But if you're down here at the cold temperature, low pressure, you would definitely see it subliming, going from a solid to a gas. Now, terms, you have freezing. Freezing, of course, is going from liquid to solid. So freezing is going to be going across this line. Melting is just going the opposite direction from solid to liquid. And condensing is going from vapor to liquid. Evaporating is going the opposite direction. And there is a term that's the opposite of sublimation, and I don't recall it. Does anybody remember that one? Excellent. Well, Jordan.
So there's this viral video going on that takes water and they freeze it, but it's still in a liquid state, and then they tap it and the water freezes.
Okay, now we have to clarify his wording here. They take water and they cool it to a temperature that's below its freezing temperature. And then they tap it and it suddenly freezes. And that is something that is certainly possible. Now, to understand it better, I'm going to go a different way. It's the same. Do you have questions as well, or you got the word, Gabriel?
Deposition.
Deposition? Okay. Like vapor deposition then. Okay, so let's take something else that we can all do and we should not. If you take a nice brand new mug that has a nice smooth surface inside, and you put water in that thing, I don't think that really matters if it's distilled or not, but you can probably do it better if it's distilled water. Deionized distilled water, and you put it in the microwave and you turn it on, and instead of putting 1 minute, you put in 1 hour. And then you come back, ding, oh, my hot water must be ready, and you take it out. It is possible that you have liquid water in there that's not boiling. Now, of course, if you left it for an hour, it would have boiled. But it's possible that you could have liquid water that's above 100 degrees Celsius and not boiling. Because you have to, and we'll see this here, you have to have these little bubbles form, and then when the bubble forms, as the temperature increases, you have higher vapor pressure in that bubble, it grows, density gets below the density of water, and it floats out, and that's boiling. But if you don't have anything to create those bubbles, to nucleate them, then you can have a superheated liquid. And this has really happened. People put their mug in there, they heat it in the microwave, and they take it out. And as they take it out, the whole thing goes poof and boils and just scalds the bejesus out of them. Right? It's dangerous. That's why we shouldn't do this. Or if you do, use something like a long pole to pull it out, Why does that occur? Because you have to have something to cause the start of the phase change. If you have a nice smooth surface, you don't have any scratches or anything that can help to nucleate the little bubbles, and you can get up to 105, 110 Celsius without having it boil. And the same thing occurs when you're cooling. You can get it down below 0 degrees Celsius without having it start to form ice crystals if you have nothing in there that's going to start the process, nothing to disturb it. And so then, of course, if it starts boiling, it boils rapidly, and you have superheated water that's suddenly steamed that scalds you with the microwave experiment. I know Dr. Miyashiro, our music teacher, studied physics as an undergraduate, he and his son did this for his son's science project last year with the super cooling water and seeing how much lower than 0 degrees they could get it before they formed the ice crystals. And so if you're going to heat water in the microwave, it's still safe to do it, but just make sure you have a scratched coffee mug, okay? If it's scratched, you're going to have the scratches will nucleate boiling and it won't get hotter than 100 degrees. If you're in chemistry lab, what do you do in chemistry lab? You put boiling chips. What's a boiling chip? Yeah, it's a little piece of rock that's rough, okay? There's nothing special about it. It's not some special material. It's just rough rather than smooth, so that you're going to have little places for the trapped bubbles. Okay, so let's have our second clicker question. Which transition is impossible? To move from solid to gas without going through liquid, to move from liquid to gas without having a phase transition, or move from solid to liquid without going through a phase transition? I had to think about this enough times for Yes, 41. Not yet. There we go. Okay. See what we got here? 10, 12, and 27. This top one's a 10. So let's go back to the previous slide rather than having a student answer. So let's see if we can go from solid to gas without crossing one of those red lines. So solid is here, gas is here. Can we go from solid to gas without going through? No, because this line goes up here and continues. So that one is not possible. You have to cross a phase line. Oh, actually, wait, that was to liquid, but it's still not possible, but I went to gas. To go to liquid, you would still...
No, it is.
He said, what is impossible is the question.
Which transition? Oh, okay, good, because there were two answers that... I was going to say there are two answers that are not possible, which is impossible. Okay, so yes, let's back up. Going from solid to liquid, if you go across that red line, that's a phase transition. If I come up here, it's still going to have phase transition before I get down to the liquid. So I have to have a phase transition to go from solid to liquid. So this here is...
C is impossible. You can't go from solid to liquid.
Well,
You can go from solid to gas without going to
A's talking about.
wait, does it say without?
Yeah.
Oh, without liquid. What?
solid.
My reading comprehension. Let's blame it on staying up late to watch the Raider game last night. Because my reading comprehension is blowing. Okay, solid to gas. What if they're going solid to liquid? Solid to gas without going through liquid. Solid gas without going through liquid, yes, right there. Possible. Okay, liquid to what?
It's down below.
Down below.
That's-
Down below.
It's both. This here is, it's not liquid. Okay, move from liquid to gas without a phase transition. So liquid to gas without a phase transition, that's what this green light is line is doing. And then solid to liquid without phase transition. And so that's the one that's impossible because, yeah, this or this, both a phase transition. Okay. Whew. Made it through that with a lot of correction from my students. Good thing I didn't have somebody answer. Actually, it probably would have been smoother. Okay, boiling. Boiling, like my body is doing here. You guys know about Colonel Sanders, right? Colonel Sanders was a Kentucky colonel, which is the same idea as being an admiral in the Nebraska Navy. You guys know what an admiral in the Nebraska Navy is, right? Mike Menard is an admiral in the Nebraska Navy. It's an honorary title for something ridiculous. In Texas, you have a Yellow Rose of Texas. I think that's only applied to women, and they have a similar one for men. But they're honorary titles to say that the state esteems you. So Mike Menard was given this honorary title. He can marry anyone because he is an admiral in the Nebraska Navy. True story. He's done lots of marriages. So, what did Colonel Sanders do that made him famous? Yeah, Kentucky Fried Chicken. Now, what he really did was he came up with a recipe for cooking chicken in a pressure cooker. And that allowed him to cook a chicken in like a couple hours instead of 6 hours. I'm a vegetarian. I never cooked a chicken in my life. I don't know the process here. But it was a much faster way of cooking chickens. And then he went barnstorming and sold people his pressure cooker and threw in the recipe as an add-on. So what does that have to do with this? Pressure cookers. The idea of a pressure cooker is that you enclose your chamber and allow it, as you heat up the temperature, the pressure goes to higher and higher pressures. But as the pressure goes to higher pressures, the boiling temperature goes up and up and up. And so what he was doing was cooking the chicken at a higher temperature because of the pressure cooker. Now, probably a lot of you guys have pressure cookers at home. I know my mom did. It's all great until the pressure cooker blows up. I don't know how many of you got pressure cookers blow up, but yeah, that makes a mess. But that pressure cooker, you put it on the stove, you turn on the burner, it gets hotter and hotter. It's got a little pressure gauge that tells you how high the pressure is inside, and you can cook things faster. So let's talk about why that occurs. You have, for boiling, you have your little air bubbles. You know, if it's normal water, you probably have air bubbles already in there. Hot tip, if your fish can live in there, there's air bubbles, right? So as you heat it up, you will have the partial pressure of water. The pressure the water makes if it filled the chamber goes up with temperature just because of the ideal gas law. And so you'll have water vapor that starts invading those little air bubbles. And the hotter it gets, the more vapor from water goes into the air bubbles. And the air bubbles, you have more molecules. They expand to keep the pressure the same as the pressure around them. But if you get to the point where the partial pressure of water is equal to the atmospheric pressure, then you can't have it expand anymore to, get the pressure down. And the bubbles just float out of the water, and that's boiling. And so if the atmospheric pressure is higher, you have to go to higher temperature to get that partial pressure up. And so that means you boil at a higher temperature. So here's the data. Now, I put relative humidity for the title. Relative humidity is these calculations down here. But this is showing two things. VP is equal to the vapor pressure, and SAT VD is the saturation vapor density. Both of those are going to go up with temperature. So the higher the temperature is, the more pressure that water vapor would have in the vapor stage. And so the boiling point occurs when atmospheric pressure is equal to the vapor pressure. So at 100 degrees Celsius, at one standard atmosphere, 1.01 times 10 to the fifth pascals, water boils. But let's say you have the distinct misfortune of living in Denver, Colorado, where right now they are, really running into that Oakland Raiders juggernaut. What's special about Denver? It's the mile-high city, which means that there's less air above them. And we studied before, the air pressure is the result of the weight of the air above you. So the air pressure there is lower. In fact, the air pressure in Denver is about 8.1 times 10 to the fourth pascals. That's the air pressure in Denver. Now, you can understand why they root for the Broncos, because with that lower pressure, there's less oxygen in the air. It causes mild, okay. Everything's true except for the mild brain damage part. Obviously, that's a joke. But because it has a slightly lower pressure, what is that going to do to the boiling temperature of water? Lower it. What would you guess to be the boiling temperature for water based on this table? Okay, somebody said roughly 80 something. Notice 80 is 4.7 times 10 to the fourth. That's far less than 8.1 times 10 to the fourth. Yeah, it's going to be somewhere here, say about 93-ish degrees Celsius would be your boiling temperature for water if you're in Denver, because of the decreased atmospheric pressure. And if you decide to hike to the top of, Long's Peak, well, at the top of Long's Peak, you're another, mile up or something? Almost 2 miles up? Is that right? Yeah, it's almost 2 miles higher than Denver. And so the air pressure is much, much lower. Hence, the boiling temperature at the top of Long's Peak might be somewhere in the ballpark of 80 degrees Celsius. So you bring a meal that you want to cook at the top of Long's Peak, you're going to be cooking for a while because it's much lower temperature, unless you brought a pressure cooker. I only got half a minute. Great. That brings us to the topic du jour, heat. Let me just say that there are three fundamental forms for heating. You have radiation, which is electromagnetic rays. Light is a form of electromagnetic rays. So light is a form of heating. We have convection. Convection is heat being carried by an intermediary material. So like if I put my hand over a flame, my hand gets hot, not because it's touching the flame, not because of the radiation, but because air was heated by that flame and that hot air expanded, right? P equals nRT. T goes up, P stays the same, V drops, it became less dense. And so it floats upward and hits my hand. That's convection. And the last one is conduction, touching something that's hot. That's the one we usually think about. So we will pick up with those next class period.